Okay, let's talk a little bit about electrophilic aromatic substitution reactions. And so, if you remember from last time when we talked about aromatic rings, they're extra stable. There's some extra stability about them being in that fully conjugated system that makes it be that normal reactions that would typically react with pi bonds, such as electrophilic addition of bromine to a double bond, that doesn't occur with the benzene ring. And as we'll see in a moment, part of that is that if you break the aromaticity, that's not a favorable process. Instead, you want to be able to maintain it. We're going to see there's a mechanism that allows that. And what scientists observed is when you throw in something additional, you're able to make the bromine finally electrophilic enough for it to react with the benzene ring. However, instead of an addition reaction, you see what we would call a substitution reaction occur. The hydrogen that was at this spot right here disappears and is replaced with the bromine instead of a second bromine being added and the hydrogen remaining. And we can already see, if you think about it, the benefit to that is that by eliminating the hydrogen that's there, you're able to return the ring back to a aromatic ring system. So what we call this reaction is electrophilic aromatic substitution. And we're going to find there's a bunch of EAS reactions. We can do bromination, chlorination, nitration, sulfonation, alkylation, and acylation, which is the acyl group or the C double bond O with something attached to it. Now, if you notice in all of these reactions, the aromaticity is maintained. And that's, once again, that's the reason what drives this reaction is that you're able to return it back to an aromatic ring system, which provides energy and stabilization, or I should say it minimizes the energy and provides stabilization. Now, why the iron? Why does the iron help it out? Well, the reason for the iron, or the role that it plays, is it's able to make the bromine atom even more electrophilic. We already know that a bromine can function as an electrophile with a pi electron. We see that in normal alkenes reacting with bromine. In order for it to attack the more stabilized p electrons that are in the aromatic ring system, to attack one of those pi bonds, in other words, you need to make that bromine electrophile even more electrophilic. In the presence of iron, and oftentimes I just tell students, and I myself just write FeBr3 as the catalyst. So you can throw in iron directly because when it comes into contact with bromine, the other reagent, it actually forms the catalyst that you need. Now, you could also just add the FeBr3 directly. Now, what does the FeBr3 do? Well, it's this kind of it's got these three groups around it in this kind of triangular shape. And what happens is the bromine molecule, the diatomic bromine, is able to attack, is this kind of nucleophilic attack with one of its pi electrons. So this is you could almost argue, is the more electron dense bromine, even though they are the same atom. That is going to donate its electron density to the iron atom. In doing that, this other bromine, which is the one you would think of as the more positive bromine, it's able to become even more positive, because you can think of it as being in equilibrium with the bromine atom having lost the electrons to the other one and becoming this cation structure. Now, that doesn't directly form, but that's an indicator. That's one way of showing that bromine now has more positive charge to it, more capability of being an electrophile. So it's essentially the mechanism of the reaction essentially comes down to a nucleophilic attack followed by a proton transfer. That's the general mechanism of an electrophilic aromatic substitution. So the first step is a nucleophilic attack. So you need an electrophile to be attacked by the benzene ring. Now, it's the benzene ring that's acting as the nucleophile. It's the other thing that's going to be the electrophile. Whatever that thing is, depends on what type of EAS reaction that we're doing. In this case, we're doing bromination. We've got this bromine molecule that's been activated by the catalyst FeBr3. So the first step, the electrophilic bromine, is attacked by the pi electrons, and the rest of the catalyst, including one of the the other bromine atom from the Br2 molecule falls off. In doing that, you generate what we call the sigma complex, which is essentially the initial carbocation that forms in resonance throughout the rest of the ring structure. And we're going to use this idea of the resonance of the sigma complex to discuss some other aspects of electrophilic aromatic substitution later on in the course. The second step is a proton transfer. So if you recall, in order to do that, it's an acid-base reaction. You need a base to deprotonate whatever the species is that's losing the proton. This deprotonation occurs by essentially using that chunk that fell off of the activated bromine. It acts as what we would call a sort of Bronsted base. It's able to accept the proton from the sigma complex, which releases the electrons that hold on to that proton so they can come back down and reform the double bond and thus return the ring to an aromatic ring system and provide, once again, that lower energy stabilization that aromaticity provides. Now, the reason why it comes from the sigma bond, now you could also draw it coming from one of these lone pairs. You just have to show then that this other bond falls off. You'd have to do two arrows. So sometimes some scientists just write a single arrow of the sigma bond between the iron and the bromine falling off and attacking the hydrogen. Do note that it is falling off. So the FeBr3 returns back to its original state, thus it's a catalyst. It doesn't get consumed. And what's generated is this extra bromine atom that was part of the Br2 molecule now is attached to the proton that was deprotonated from the benzene ring, or I should say the sigma complex, to return that ring structure back to aromaticity. So that's essentially the process, not only of specifically bromination, but as we'll see at the end, that's the general mechanism. An electrophile attacks the nucleophilic benzene ring, creates a sigma complex that is deprotonated by some base in solution that returns it to an aromatic ring system. Now, if you think about the two pathways that could still be possible, because there's still bromine floating around in solution, why doesn't it attack the carbocation as a nucleophile and do essentially electrophilic addition? And it has to do with thermodynamics. So we talked about, like with the conjugated dienes, this idea of kinetics and thermodynamics. This result is due to thermodynamics. The substitution product, because as you can see, the kinetics are roughly the same. There's no difference in the activation barriers, but there is a difference in the overall energy of these products. And thermodynamics tells us the lower energy product will be the more favorable one over time. So if you give it long enough time, heat it up a little, you're going to form the more stable product. And that's what we know is going to happen. We're going to form the substitution product, thus return the ring to aromaticity and make it a way more energetically stable, lower energy product than if you were to do the electrophilic addition and form the addition product and attack with a bromine nucleophile. And we're just going to finish up with a few more things. It doesn't have to be FeBr3, AlBr3, or aluminum bromide. That can also do the same thing. Well, in fact, we'll see an aluminum catalyst for another EAS reaction where it's more typically used. Another thing to point out is that typically we can do chlorination also. And oftentimes AlCl3 is the catalyst reagent that's used for chlorination. I think you try to match the halide that's on the metal catalyst species with the halide that you're trying to do for halogen. You're trying to add or substitute in the EAS reaction. So you don't want to mix it too much. But I think I've even seen mixing. It's just rare. So the more common rule is if you're doing chlorination, put AlCl3. If you're doing bromination, put either iron bromide or aluminum bromide, FeBr3, AlBr3. We do not see fluorination or iodination occur. Fluorination is too violent, and so it's not safe to do. And iodination doesn't happen because it's too slow and doesn't have a high yield. So once again, chlorination, exact same mechanism, because the only difference between chlorine and bromine is the identity of the element, it has the same exact, molecular structure, or at least the same Lewis bond structure, the way it looks with the lone pairs and the bonding. So the species look almost identical, except there's a Cl instead of a Br there. But you go through the same thing. The ring attacks the electrophile and it turns into the sigma complex, and then some base, in this case, the same thing, the sigma bond between the other remaining halogen, in this case chlorine, attached to the catalyst. That sigma bond falls off the catalyst and steals the proton from the sigma complex, returning the AlCl3 back to normal so that it can go back and reattach to a new chlorine molecule and get the process going again. Once again, the general mechanism, as we just showed with the chlorination, this is just true for all of these EAS reactions. There may be different reactions that create the electrophile. The electrophile just may be what you throw in. Most of them have a catalyst that reacts with something to generate the thing that actually acts as the electrophile. But the general mechanism is an electrophile attacks the nucleophilic benzene ring, or you guess, since we call it a nucleophilic attack, you could say it the other way. The benzene ring attacks the electrophile, adding it to the ring structure, creating the sigma complex here, which is in resonance. And then a proton transfer occurs. Some base in solution steals the proton that was once at the carbon that the electrophile is at. And those electrons are able to fall off and fill in this carbocation, returning the ring to an aromatic ring system. One thing to note before we end is you see the sigma complex in all these three examples that we've seen of the mechanism. And it always starts with the carbocation forming here and then moving around in resonance to the other side. I want to emphasize you do not have to draw that. In fact, some students just think that's actually part of the reaction, like it has to like move around to get to the right spot for the reaction to occur. The base could have stolen, or at least I could say, you can draw the reaction with the base stealing a proton immediately with this structure drawn as it is here. You don't have to go through all the resonance forms. They're just taking the time to show you what all the resonance forms are, not saying you have to like go through some stages to get to the right one for the reaction to finish. To remind you, resonance forms aren't things that are existing over time and things are transforming into them. They're the only way we can draw what is this weird hybridization smearing out of electron density that just simultaneously exists. In other words, all three of these structures are really just are not really the exact true structure, but rather a kind of melding of them is. And so really there's a slight partial positive charge here, slight partial positive charge here, and a slight partial positive charge on this carbon with a slight double bond character between all four of these bonds. Because you can see throughout the resonances, sometimes they have a double bond, sometimes they don't. So it has an in between, not quite a sigma, not quite a double, in that resonance structure, that hybrid structure of what it really behaves like. And so that positive charge is throughout the whole ring system, just partial positive charge located at these three carbons. That's what the resonance structures show you. Well, that's it. Hopefully you are able to kind of see what the general mechanism is. We're going to go through nitration and sulfonation in lecture, and then in a later lecture we're going to go over the rest of them, which are the Friedel-Crafts reactions, alkylation and acylation, and some of the intricacies of those. But as you'll see when we get to those as well, it's the same mechanisms over and over again, just different electrophiles, different catalysts. Anyways, I'll see you later.